thank you all. Thank you to the organizers for the chance to be here. It's a beautiful place, and it looks like a great program. So the work I want to tell you about today is, I guess, has its roots in like a very standard manifold topology question, which is, this dichotomy between sort of geometry and algebra. Maybe isn't really so much a dichotomy. We know that, in fact, oftentimes the two go hand in hand, right? Situations in which you have strong geometry, you often have strong algebra as well. And we want to think about a question of Borel that basically asks, under which circumstances does strong enough algebraic topology make your manifold sort of behave like a geometric manifold, even though it actually doesn't have geometry? So to provide that context, let's talk for a minute about some topological rigidity from geometry. Actually, maybe let me interrupt myself first. First of all, can you guys hear me okay? Okay, and is board writing visible? Okay, so I should mention, I'm going to write on the board, but for pictures of diagrams and whatnot, I'm going to use the projectors on the side. Okay. So I'm going to start with sort of a pseudo mathematical statement, which is that if I have two manifolds, M and M prime, and they're both nice, I'll just say for simplicity, geometric quotients of Rn. So maybe they're flat manifolds or hyperbolic manifolds, something like this. Then homotopy equivalence implies diffeomorphism. I mean, indeed, under the right circumstances, we could really probably say isometric, but I'm mostly going to be thinking about homeomorphism and diffeomorphism here, so I'll just leave it at diffeomorphism. Okay? And not only is that true, but because they're quotients of Rn, all their higher homotopy groups vanish, so they're homotopically determined by pi1. So if the homotopy type determines the diffeomorphism type, then the point is that these are entirely determined by pi1. Okay? So let's try to make this a bit more concrete. What do we mean? Well, any surface, for example, that's not equal to the 2-sphere or RP2 will be a quotient of Rn, any connected surface. And we could also look at, for example, flat manifolds, hyperbolic manifolds, or solved manifolds. And here, this type of rigidity statement, well, in the surface case, this is basically the Dane-Nielsen-Baer theorem. In the flat manifold case, this is work of Bieberbach. It's classical, or classical-ish, I guess. Hyperbolic and solved manifolds, that's the same color. This is Mostow rigidity. Okay, so sort of actually first established for solved manifolds, and then later for hyperbolic manifolds over time. Okay, and I said that somehow Borel is going to enter the story. And so Borel is looking at these results and saying, these are interesting results, and is really sort of focused on the idea that the topology is somehow captured by pi1. Yeah. So for example, to take a baby example, the torus is going to be our sort of prototypical character today. Definitely a nice quotient of R2. Its fundamental group is z squared. And one thing you might say is, well, of course its fundamental group was going to be a product. It's a product S1 cross S1. Borel is thinking it's a product because its fundamental group is a product. This is the type of information we're thinking about encoded in the fundamental group. Okay. So Borel writes to Serre, do I have my clicker? Yeah. And saying, it's a wonderful proof, it's totally non-trivial. He has a bone to pick, though. My French isn't great. I know that the demonstration means proof. Does anyone know what épouvantable means? Terrible. Oh, God. Oh, yeah. OK. So I double-checked. Doesn't love the proof. His objection is that it can't be simplified entirely, but it could be simplified significantly by using covering spaces theory better. Okay? And so it goes further to say, in fact, does this just hold purely for sort of homotopical reasons? Right? We're saying it's a homotopical phenomena that if you're in this class of manifolds, your homotopy type determines your smooth type. So forget the geometry. What's the homotopical condition? It's that you're a quotient of something homotopy equivalent to Rn. That means you're a quotient of something that's contractible. So he says, does this hold for aspherical spaces, quotients of contractible spaces? Okay, back. Okay, so that brings us to think about aspherical manifolds. So for a moment, I'll just let M be a manifold still, although this definition works for an arbitrary space. So I remind you that the space M is aspherical if all of its higher homotopy groups vanish. Okay. So we can have interesting fundamental group, but no interesting higher homotopy groups. And it's a simple exercise using Whitehead theorem and Hurewicz theorem that if you have a CW if M is a CW complex, in particular if it's a manifold, but if it's any W complex, then this is the same thing as saying M has a contractible universal cover. Okay. So Borel is interested in this problem for aspherical manifolds. And I just want to point out, in terms of examples of aspherical manifolds, well, certainly all of these nice quotients of Rn are going to be aspherical. Also, by definition, any k pi 1 is a spherical space. But in general, if you give me a group and I try to build some k pi 1, we can do it. But it's typically not going to be compact and not going to be a manifold. The process is sort of quite nasty, right? So for a long time, the main examples of closed aspherical manifolds were these geometric quotients for Rn. So we'll revisit that theme in a bit. Okay. So before I write down Borel's main question, I'll pause and see if there's any questions so far. So is this my eraser? Yeah, okay. All right. So, there's nothing wrong with it. It's nice. There's rags too. I see. There we go. Okay. I'll rag this part later. All right. So what Borel asks essentially in that letter to Serre is for closed aspherical manifolds, does homotopy equivalence imply homeomorphism? Okay. You'll see he's even saying homeomorphism here. And I want to point out that at this time, this is pre-exotic spheres. At this point, we don't really know the differences between homeomorphism, diffeomorphism, et cetera. Borel there was a natural equivalence to choose there. And this is actually an open question still. It's true in dimensions 3 and below. It is known for some fundamental groups in higher dimensions, but it's open in general. Okay. And so this is the question Borel asked, but it's not the question that I want to talk about today. So the modification of this is if you have in geometric context, we said homotopy equivalence implied isometry even potentially, but at least diffeomorphism. So could we be greedy and ask about the smooth setting, and ask about does homotopy equivalence for closed aspherical manifolds, smooth manifolds, imply diffeomorphism? Okay. And so the answer now is yes for dimensions less than or equal to 3, basically because homeomorphism and diffeomorphism there are going to coincide. And it's no for all dimensions greater than or equal to 5. And the first examples, I brought up Milner before, the first examples are you take an exotic 7 sphere, connect some of it with the 7-dimensional torus, and you get an exotic 7-dimensional torus. Okay, so these are the first known examples. Apparently, Borel was quite relieved that happened to write homeomorphic in the letter. But it turns out there's exotic tori in all dimensions n greater than or equal to 5. It's due to work of Sang and Wall. Or I guess, well, that's a bit of a simplification, but that's what I'll write down. That's where you'll find the actual final statement. Okay. And so the question, in this case, the obvious missing point is dimension 4. Okay. And so the answer surely must be that the answer is no still in dimension 4. But for some reason, it's not amenable to the same techniques as in higher dimensions. And what's going on in these situations is that you're essentially, in a sense, classifying the smooth structures on these manifolds, the diffeomorphism types, or at least providing enough information about them. But we don't have anything like that in dimension 4. We can sort of individually try to construct an exotic smooth structure, but we can't sort of get this big zoomed out picture that works more broadly. And so, for example, we don't know if there are exotic smooth structures on the 4-dimensional sphere. So the main result I want to tell you about today is that the answer is also no in dimension 4. So this is joint work with Mike Davis, Jingyang Huang, myself, Danny Ruberman, and Nathan Snukian. And I'll say there exist, for now I'll just say pairs of closed smooth aspherical 4 manifolds that are homeo, but not diffeo. Okay. So that's the main result I want to talk about today. Yes, please.
In the T7 example with 7 spheres, if you take a finite cover that manifold, it becomes standard. Do you know anything about?
Yes, so this is a great question. So, embedded in the history, this question is, right, so just to make sure that it was audible for everyone. In these cases that we were saying, for example, in dimension 7, they're going to be covered by, universal covers, they're going to be covered by the regular 7-dimensional torus. This relates to questions like the annulus conjecture and all these other important problems. And in our case, no, the universal covers will not be, I don't think universal covers, sorry, I believe they're not covered by sort of any familiar standard, either the 4 torus or anything like that. Is that, or sorry, and their universal covers are not going to be R4. Yeah, sorry. Oh, finite cover. Oh, I believe the answer is no, and not just intuitive. I think that you could prove that pretty easily, but I'd have to think a tiny bit. Yeah, I believe. Yeah, it's a good question. Yeah, thanks. It's a good question. Yeah, other questions about the statement or anything before we say a bit about the idea and the plan? Yes, that's right. Exactly. There, I have to think about that. I believe, I don't know. I believe, intuitively, I believe the answer is no. I think that it's easier to probably to say something about at the finite step, at the finite stage, but I believe their universal covers are probably distinct, but it's not totally clear. I'd be happy to revisit the question after going through the construction, because then maybe it'll be more or less evident why that's not clear. Yeah, thanks. Good question. Okay. So, and maybe I'll just say right now, this is going to involve quark twisting. And so what's going to happen is if you take some large cover, the quark twists always just lift nice little quark twists. There's sort of no topology to unravel. And I don't expect for any reason those quark twists to sort of dissolve just in some sufficiently high cover. But yeah. Okay, great. So that already brings up one of the themes. And so maybe to set the stage for the rest of the discussion, let's explain why this, or talk about why this doesn't fall from sort of more standard techniques that have existed so far. For one thing, most four-dimensional exotic phenomena, the actual constructions are cut and paste operations, surgeries on tori, or summing together different manifolds. And these work best in a simply connected setting if you need to preserve the homeomorphism type. And aspherical manifolds, closed aspherical manifolds, are never going to be simply connected. They're always going to have, in fact, pretty interesting pi1, because again, that's sort of encoding all of the homotopic information. So it's hard to preserve the fundamental group during surgery operations on aspherical manifolds, unless, for example, your surgery operation happens in a contractible region that doesn't change pi1. So that's going to be a natural sort of push towards thinking about quarks. Another issue is also when you think about the relative setting, they're already known to exist exotic smooth structures on aspherical four manifolds with non-empty boundary. Those are not as difficult to produce. But there's two problems. One is that just because I have, let's say, some aspherical pieces with boundary, if I glue them together, I might not get something aspherical, right? Like sort of simple cartoonish example is the disk itself is aspherical. The natural way of taking copies of it and getting a closed thing would be to double it. And that's clearly very spherical. Okay. And the other problem is that often trying to close up manifolds this way tends to break the smooth structure, the exotic smooth structure, and sort of collapse it back to a standard one. And that's actually the biggest point I want to try to sell today, which is that the construction we're going to talk about is surprisingly effective at taking some interesting exotic smooth structures on a compact four manifold and preserving a lot of their features while closing it up to a closed four manifold. Okay. So the plan for the rest of the time is to basically walk through the idea of the constructions and the proof. So the first thing is we need some building blocks. We're going to start with some compact aspherical four manifolds with boundary. Exotic aspherical x prime with boundary. And then we're going to use this beautiful construction due to Mike Davis called the reflection group trick. So this comes from sort of study of geometric group theory with Coxeter groups, and basically can take sort of compact aspherical manifolds of boundary, or even not necessarily manifolds, just spaces, and build sort of natural closed ones from them. And so this reflection group trick is going to give us some closed Q of x and Q of x prime. And they're still aspherical by construction. And so the final step is to say, okay, if these building blocks were exotic, we want to prove that the results are still exotic. Okay, so that's our plan. So, building blocks. Well, I already hinted at the first main idea of these building blocks. So we're going to want them to be some compact four manifolds that are aspherical. And we really want some exotic smooth structures in them. So I'm going to start with the maser quark. And then I'm going to do something funny, which is, here we go. I'm going to look at a knot in its boundary. And usually if we see a knot in the boundary of a four manifold and you're a manifold topologist, you just can't resist attaching a two handle to it. But we're not going to quite attach a two handle. Ooh, so sorry. Instead, we're going to attach what you might call a genus one handle. So this is F times D2, where F is genus one surface with one boundary component. And so the boundary component, you can think about F as being attached along, boundary component of F is attached along this knot in here, and then you cross by D2 to make the attaching region a solid torus, and you thicken this surface. Okay, so this is going to be the basic structure of our building blocks. Here's some Kirby diagrams for them if you're interested. These are not the most enlightening ones. We'll look at more enlightening ones in a moment. But the point is that this maser quark can basically be cut out and re-glued, and in fact, it'll change the smooth structure in this case. Okay, so the examples, the construction we're looking at come from a paper of I wrote with Lisa Piccirillo, and sometimes I forget what year it was. It was 2019, but it was for some reason on basically New Year's Eve. There's that saying, if a preprint falls on New Year's Eve, does it make a sound? Okay, so there exists compact four manifolds, X and X prime, in R4 that have the following properties. So they're going to be constructed this way. I'm sneaking one of their first properties into the statement here. The manifolds we're constructing actually sit inside of R4, and that's going to come up later. What properties do these have? They're both homotopy equivalent to the torus. And I'll just sort of roughly sketch the reason why. Well, if we're attaching F across D2 to something contractible, first of all, the sort of D2 factor can be sort of deform retracted back onto just the copy of F cross 0. So it looks like we're attaching this surface to something contractible. But if you're attaching a surface to something contractible, then that's like coning off the boundary of the surface homotopically. So we should get something which looks basically like the cone on the boundary of this. So this should be basically a torus. Okay? So they're homotopy equivalent to a torus. And that, by the way, ensures that they're aspherical. The second condition, is this too low? This is probably too low. Let me move up. Thank you. Go to sleep, go to sleep. The second condition that we need is that they're homeomorphic. And for this, using the quark twist plus the fact that quark twist homeomorphism, or diffeomorphism of the boundary, extends to a homeomorphism of the interior. So maybe let's just take a detour for a second to look at some more diagrams. What we have here on the left is a symmetric looking picture of the maser quark. And in light blue here is a neighborhood of some knot K that's of interest to us. And so we're going to attach this thickened surface to it. And what you'll notice is that the boundary of the maser quark, that would be, as a Dane surgery description, you turn this dot into a 0, and then it's symmetric. You reverse these roles, so you put a dot in the bottom, and you get X prime. Okay? And so the quark twist is what is relating to these, and because it's contractible, as we said, application of Friedman's work is that they'll extend to homeomorphism. So in fact, we get a homeomorphism of these sort of rel boundary, because there's a natural boundary identification of them that extends to a homeomorphism of the interior. Okay. So then the third bit of information we need about these is that they are not diffeomorphic. And shorthand for why these aren't diffeomorphic, I'll just say some gauge theory, and I'll give a bigger explanation in a second. But the idea is that we're going to study the genera of surfaces embedded in these manifolds. Okay? So it turns out that one of these manifolds, X prime, is going to contain a smoothly embedded torus that generates its second homology. In fact, the curve K is going to bound a disk inside of the maser quark, and so you sort of cap off the core F cross 0 with that disk. On the other hand, X will not. Okay, so how do I want to say this? I'll say, so H2 of X prime, is generated by an embedded T2, but any T2 in X, I'll just say, is null homologous. Okay. And so how do we prove that? Well, there we're using the fact that you can construct a Stein structure on X. So details of this doesn't matter, but the point is, if your manifold emits a Stein structure, which you can establish using Gomp's work of Gomp and Eli Oshberg on Handel structures for Stein manifolds. And so if you can construct such a structure, you get some constraints on the genera surfaces in your manifold via the adjunction inequality. And if you just run the calculation, you find out that the generator of H2, the minimal genus, is going to be 2, not 1. Please. Great, yeah, so in this particular case, it will be, and that's going to be part of what makes it possible to embed it in R4. So the question was what the intersection form on this is, and it's going to, it's going to be, H2 is going to be Z, and the intersection pairing is going to be trivial. But you could attach an interesting framing for this blue two-handle here. This is doing the work of attaching the thickened surface, and then this actually makes it a thickened surface instead of a two-handle. You can make this framing other framings, and everything except this will be true. Well, if you make the framing sufficiently negative. But yeah. So, does that answer that? Great. All right. So, so those are our input manifolds. And so let me pause again there to see if there's any questions before I move on to saying we've got our building blocks, but now we need to figure out how to put them together. Okay. So the recipe that we're going to use for putting these, question? No, okay. The recipe that we're going to use for putting this together is the reflection group trick. So I should have mentioned, by the way, as I'm writing the text on the board, as the talk proceeds, I'm going to talk less and less and show more and more pictures until I think the organizers would like if I completely stop talking eventually. So I'll do my best. So the reflection group trick, this is due to Davis in '83. So I mentioned earlier that for a long time, basically the only examples we had of closed aspherical manifolds were ones that arose from geometry. They were sort of natural nice quotients of Rn, or maybe not geometric quotients, but at least covered by Rn. The reflection group trick was used by Davis to produce the first examples that were not covered by Rn, and they were distinguished by their fundamental group at infinity. So it's the sort of the underlying topology there. But for our purposes, you should think about the reflection group trick as a machine for turning compact aspherical manifolds with boundary into closed ones. In reality, this trick is actually much more general. they don't necessarily care about manifolds. It really comes from geometric group theory and nice spaces that Coxeter groups act on. Okay. And this trick, there's several stages to it. So it can look a little overwhelming. So I'm going to try to demonstrate it with a running example. So your first input is some compact aspherical manifold X that not only has a boundary, but we want to put a nice triangulation on its boundary. Okay. So the running example we're going to use is the disk. And I'm not going to fully spell this out, but I'm doing some lying here. By nice triangulation, you're actually not even going to, it's not triangulation, it's actually a polyhedral cell decomposition of the boundary, but it's a special one. So they're special, but they're abundant. What you do is you take a, what's called a flag triangulation of your manifold, which basically just means if I have a collection of n vertices that are all pairwise connected, then they have to be filled in by an n-1 simplex. Okay? So for example, if I try to triangulate the boundary of the disk as a triangle, the boundary of the disk, all three of its vertices are pairwise connected, but the boundary of the disk doesn't contain the two simplex that they span. So you want no triangles, so basically. So that's just a technical condition. And then what do? You take that flag decomposition, or flag triangulation, which you can always achieve by just like barycentric subdivision. It's very easy to produce. And then you dualize it. You take its dual cell decomposition, and that's going to give you some nice, I'll call it a triangulation of the boundary. Okay, but the point is this is some easily accessible information. In our case, we're going to choose looking at the disk as the unit square, and its boundary as 4 vertices with 4 vertices is a sufficiently nice triangulation. Okay. Okay, so the keyword is flag. Okay. And next, you're going to associate to this some Coxeter group. And it's easy enough to describe explicitly, so I'll do that. So it's going to be generated by the faces in your triangulation. So every face 1, 2, 3, 4 gets a generator. And you're going to make all those generators square to the identity. That makes them like reflections. And the other condition you're going to put on, the other relation, is that S and S prime commute if S and S prime are adjacent. Okay. And that's also natural from the perspective of reflections, if you think about sort of how reflections across the x, y axes look. Oh, sorry, adjacent meaning share a top dimensional face of them. Yeah, yeah, thanks. Great, okay, so this looks like maybe a lot of information, so let's take a concrete example. Oh, sorry, this is, in case there are any questions, this is just a technical slide about the dual decomposition thing. You can ignore that. So to try to make this more concrete, I stole some toys from my son. So these might not be super visible, so we're going to be able to follow along with this too. So I have my unit disk, and I've got all of its faces sort of distinguished. And what I'm going to do is, now think about, I've got this Coxeter group, and what I want to do is build a space out of these, that this Coxeter group acts on nicely, and then we're going to take an appropriate quotient of that space to get something compact. So the first step is just to take one of our copies. So sorry to my son. Okay. All right. Oh, it's not magnetic. Thank you. Anything here? That doesn't matter. Okay. So now he's going to be really upset. Didn't even work. Okay. Not to worry. So what are you going to do? You're going to build a space that this group acts on. So for the explicit example we have from before, here's the presentation of the Coxer group if you're interested. That's just following this recipe. And so what we're going to do is glue together copies of this space by reflecting across the faces. Okay? So this is going to lead to, oops, that's the wrong enumeration. Okay. So 3 Davis space D of x. So this is going to be built from copies of my building block. So I take infinitely many, one for each element of a Coxeter group, and then I'm going to glue, via the elements of this group. Okay? So this is non-compact, but it carries an action of gamma on it. Okay, so let's look at what this does in this example. So I take the identity first, and then I look at, let's say, the bottom, and I reflect across this bottom face, and that was the element A, so I'll call that tile A. I look at the one on the right, reflect across this right edge, that's B, and I keep doing this. And if I want to keep going, I sort of take a walk filling out all the words in my group. So A and then B gives me AB here. But if I really want this to snap in nicely, like it would with those, I have a bit of a dilemma, which is that this also should be B and then A, so BA. But that's fine, because we said that adjacent faces commute. So AB is the same as BA, so this gluing works. Okay? And you keep filling this out, and you keep filling this out. And in this case, you get R2. Okay? And it carries this action of gamma, which I want to point out is, well, actually, I won't say anymore. Yeah. Okay, so that's this non-compact Davis space. Okay, and then what are you going to do? You're going to get a compact aspherical quotient, Q of x, which is this Davis space modulo the action of the commutator subgroup. Okay? So this is some finite index torsion-free subgroup, and so when you take the quotient of this, you actually get a manifold. Okay? And so just because it's fun in this concrete case, if we think about what happens when we take the quotient by the commutator subgroups action, well, for example, anytime I see A, B, C, D, that's the same as any other string containing those same 4 characters. So this, this, and this are all identified. And if you sort of check, the fundamental domain for this action will be this, 16 of these tiles. The tops and bottom, left and right, will be identified, and we get a torus. Okay? So applying the reflection group trick to the unit disk gives us the torus. So we're seeing one example of the reflection group trick giving a closed aspherical manifold based on an aspherical input with boundary. Okay, so we're going to apply this to the manifolds x and x prime that we referenced before. Okay, so let me pause there before we go any further. Okay, so this looks a little too nice. In reality, our thing looks more like this, right? Our tiles aren't contractible. They are sort of homotopy equivalent to tori. So we should think about this sort of weird looking, I don't know, monstrous looking space. This is kind of a model of what our space looks like. And we apply it to x and x prime, and we get 2 different manifolds. Sorry, we get what we hope are 2 different manifolds. Okay. So any questions about this machine for turning our compact inputs into some closed manifolds? Yeah, Mark. Let's see. I feel like this is like a general fact here. Yeah, okay, there you go. Okay, so just providing a copy. Oh, yeah, great. And I should mention, it's nice in that example to actually work out what the commutative subgroup is, and it's a copy of z squared, but it's not the usual action. It's the one that sort of is this kind of weird, bigger 16-tile mover or rounder. Okay. It depends a lot on the triangulation in the sense that the more complicated the triangulation, the more complicated everything else will be. But also, most of what I said applies, for example, even if you don't have a nice triangulation. And if you don't, then, for example, you can get something spherical. Like if you take the disk as the triangle, you'll get the sphere. If you take the pentagon, you'll get a higher genus surface. So this type of relationship. Yeah, great question. Okay, so with the remaining time, I'm going to sketch a little bit about the main proof. Yes, please. Yeah, so this is pretty non-trivial. It's maybe perhaps non-trivial that d of x is a manifold. The quotient will be if you know that the action is sufficiently nice. I don't know I have anything intelligent to say at the moment about it, but I will say something in a little bit that maybe makes it worse, not better. Okay. So what's the idea of the proof? Well, let's go back to take a look at our manifolds. We're going to take these inputs, x and x prime, and so we're going to set q, I'm going to sort of hop back and forth between notation, to be q of x, q prime to be q of x prime. And the first question is, are these homeomorphic? And the answer is yes, because we said before that x and x prime are homeomorphic rel boundary. So if I'm building two different buildings out of bricks where the bricks are homeomorphic rel boundary, then you get homeomorphism of the entire building just sort of brick by brick. Yes, thank you. So what I should have made clear before is that this identification of them rel boundary, they're sort of two different fillings of this common boundary. So we can use the exact same on-the-nose triangulation. So they really are just being popped and changed sort of copy by copy. Thank you. And then the other question that remains is, okay, so they're still homeomorphic, but did they accidentally become diffeomorphic? This happens all the time when you're trying to close up compact four manifolds with boundary that have exotic Smith structures. And so our approach is a two-step thing, which maybe that's worse or better, can't tell. Okay, so it's two steps. First, what you want to do is suppose that you did have a diffeomorphism between them. Well, our first step is going to be to show that this lifts to a diffeomorphism of these covers, these Davis spaces. Okay. And then this we're going to obstruct. So it turns out to be easier to obstruct the diffeomorphism between these covering spaces than their quotients. Okay. All right. Okay, so mostly through pictures now, I want to try to sketch a bit about these two steps. So the first thing, let's talk about the obstruction first. Let's first see why, because basically this is going to be more of a geometric group theory argument, whereas this is just typical four-manifold stuff. So for the obstruction, we want to show two things. One, we want to show that d of x contains a torus that is non-trivial in homology. Okay? And now, why should this be true? Well, things that are true of these building blocks should hopefully still be true of the thing you're building out of them. And indeed, I'm not going to say too much about why this is true, but the point, what could happen? The worst thing that happens is when you glue together multiple copies of x prime, x prime already contains these tori. The worst thing that happens is somehow you accidentally make those null homologous, right? But there's this amazing property of this construction proved by Davis in that paper, which says that D of x is exhausted by spaces Pn, which is a boundary sum of n copies of x. So actually, there's this interesting word length on the Coxeter group, and if you imagine building out x in terms of that word length, it turns out that at every stage, the new copy of x only meets the previous copies in a ball, in a disk in the boundary. So it essentially looks like a boundary connect sum at every stage, which is sort of totally non-intuitive. This would say to Tom's point, not only is this d of x a manifold, like the gluing is nice enough that it's a manifold, it's actually nice enough that somehow at every stage it kind of looks like a boundary connect sum, but not for the same reasons. It's just a very unintuitive aspect of the construction. But it's wonderful because this, for example, ensures that the inclusions of these homology groups into the total are injections on homology. Okay? Okay, and then the second half of this statement is that we need to show that any T2 in D of x vanishes in homology. And again, that was true in x, but do we know if it's still true in D of x? And again, there we're going to use part of this property. And so let's just do a quick walkthrough of what happens here. Okay, so the first thing is, if I do have some torus sitting in D of x, then it's only going to hit finitely many of these little building blocks of these tiles, just for compactness reasons. Okay? So that means it lies in one of these subsets that's itself diffeomorphic to just a sort of linear chain of plus or minus x. And I didn't say much about why it's minus, but the reason is because you're gluing by reflections. So even if I sort of take originally all the same orientation, the quotient space, when I'm gluing by reflections, I need to change the orientation. So perhaps I'm sitting in some linear chain of minus x, x, minus x. I'm sort of smeared over their topology, right? Like perhaps this goes to like this torus plus this torus, and then like plus and minus some smeared over copies of that one. And so what we're going to do is use the fact that these sit in R4. So I can attach handles to the complement, or sorry, to the boundary of x to turn it into R4. So in particular, I can attach handles to turn it into the 4-ball. So what I'm going to do is I'm going to plug up all but one of these copies of x. And in particular, I'm going to basically check, all right, if this is going into here, I need to, and it's non-trivial in homology, it's going to have some contribution from one of these terms. Plug up all the other terms, right? So those all become 4-balls. And we said that these are actually meeting along 3 balls in the boundary. So this looks like a connected sum. So if I take x, connected sum, some 4 balls, I just get x. And so by sort of adding some extra handles to these other copies, I can sort of slurp the torus back into one single copy. And then you need to use this sort of decomposition to argue that you haven't killed anything on homology, but you can sort of bring one torus back into, or sorry, bring a torus back into one copy. Okay, so I'm almost done, but I want to pause for questions about this part of the argument before we move to a couple words about the geometric group theory side. Okay, so this is going to, yeah. Sorry, so for the sake of an argument by contradiction, we want it to not be 0. Or alternatively, you could just run this argument constructively, but then you have to do it's a little bit more awkward. Yeah, but that's right. So we wanted to conclude that, we have something a non-trivial torus in our x contradiction. Yeah, thank you. Okay, so these are distinguished, these covering spaces are distinguished by the types of surfaces they contain. And so the final step, and I should mention, in a sense, this should have been easier, right? If these were really sort of boundary connected sums and X had a Stein structure, you'd kind of want to say that something formed by a bunch of copies of X also is Stein. But it's this minus, this sort of orientation reversal that really messes with most of our invariants. And that's why this sort of topological sleight of hand was pretty necessary to get around the fact that some of these have the wrong orientation. Okay, so the final piece of the puzzle, just to say it quickly, is the lifting problem. Actually, let me give myself a bit more room. Maybe while I'm erasing this, one more comment about that proof. This proof is sort of exhibiting why this method of constructing a closed manifold from these pieces doesn't accidentally cancel out the interesting topology, because the way they glue up is sort of essentially by connected sums. Okay, so what is left is just the lifting problem. And so diagrammatically, what's going on here is we have d of x covering q of x. We have d of x prime covering q of x prime. And we're supposing that I have some diffeomorphism f. And what we want is to know that there's a diffeomorphism, that implies that there's a diffeomorphism up here. Okay. And now if we think through the lifting criterion, what's actually happening here is we have this map go down into here, and we need to make sure that the image of the fundamental group of this lies in the image of the fundamental group of this. That's just the lifting criterion. But if we take pi 1, I want to point out, just to remind ourselves, these covering maps, these are injections on pi 1. So I can think of the fundamental groups here really as subgroups of the fundamental groups downstairs. So sort of a simpler way to think about this is to say that the map induced by f takes pi 1 of d of x to pi 1 of d of x prime, where this is inside of pi 1 of q of x prime. Right, so this is naturally a subgroup in here. I want to show you it goes to the same subgroup over here. Okay? And I want to point out, these are really all the same groups. Right? The fact we've changed the smooth structure on the interior, but really we're looking at these diagrams where it's the same group up here, same group up here, same group down here, same group down here. So what we're really asking about is automorphisms of this quotient space's fundamental group. Okay? Yes, please. I think that will, if I'm not mistaken, that should sort itself out. We will get, I think that for like, I'll have to think about that for a second. For some reason I thought it was automatic, but on the fly it's not clear to me. It will be an it will be equality. And for some reason I thought for some kind of group action reason or degree reason, you don't need to worry about higher degree. So yeah, let's come back to that. Okay, so we said we want to analyze these fundamental groups and their automorphisms. And so just to sort of say that quickly, another consequence of that magical fact about connected sums, boundary connected sums that I erased, is that the fundamental group of the Davis space is just a direct sum of copies of the fundamental group of X. So in our case, whoops, that's not the thing. Oh, sorry. Yes, let me clarify that. The boundary sum on the topological level will then give us a free product on the group level. Sorry, I think I muddled the words out loud. Thank you. So this just looks like a bunch of copies of Z2. And what do we want to show? We want to show basically that all Z2s in pi1 of Q come from pi1 of D. Right, so these are the only Z2s, and that'll be sufficient to show that you have this containment. Okay, so let me just finish with a picture then. How do you show this? Well, we need one more topological input, which is we need not only for our triangulation to be flag, we need it to have no squares. So we saw before that squares in the reflection group trick give rise to tori. If you get rid of those, then you actually have no Z2 subgroups in your commutative subgroup, okay? And so to finish off the proof, I'll just say the very rough idea in 30 seconds. What do? Well, suppose I had some Z2 subgroup which did not strictly come from the cover. You can rule out it not coming from the cover at all by the sort of no squares business. But what might happen a priori is that I have a Z2 subgroup where part of it comes from the cover, and then part of it meanders into the rest of the fundamental group. We want to show that the Z2 actually has to be strictly contained in each tile, essentially. Okay? And so what do? Well, if alpha and beta were some curves that generated some Z2 subgroup in the quotient space, then I can look at lifting them to the cover. Alpha is going to lift to a loop that's just contained in a fundamental domain. But beta, if it didn't sit in the covering space's fundamental group as a subgroup, then it does not lift to a loop. It lifts to some path that ends in a different fundamental domain. And so there's a natural group action that basically says, walk over along that path, run around the translate of alpha by the deck transformation, and then run back along beta. And if these really do commute, if alpha and beta really do commute, then that loop up there is supposed to be freely homotopic to alpha. But we can see that if beta is not coming from the cover, then eventually it's going to translate this alpha far enough away that they're definitely distinct, and we get a contradiction. So this just involves sort of looking at this group action on the covering space. OK, so let me wrap it up there. I'll end with the picture of the no squares thing. Thank you, guys. Yeah. We can engulf the. OK, yeah. So just to repeat the question, there's sort of two perspectives, right? Like you can think about what is the actual. Forget about the Davis cover, which is some finite index cover. What about the, sorry, no, it's infinite index, but it's not the universal cover. Look at the universal cover, and that's going to be some contractible space. And you could ask, is it R4? Is it an exotic R4? Can you sort of, if you look at the actual construction of the universal cover, you'll see a bunch of copies of your quarks, right? Because my building blocks were quark plus basically a torus. And so when you unfold that torus, you sort of get like a calligraph-looking thing with a quark at every vertex. And so you ask, right, what's going on with these two pictures? And I think the thing that reconciles them is that I think the universal cover is not R4. So you'd have to do a little bit of work to confirm this, but the fundamental group at infinity is going to, of the universal cover, should pick up some of the non-trivial fundamental group from sort of the boundary of the quark in some sense. Like if you just actually run the Davis construction with the quark, forget the actual sort of genus 1 part, you will get some contractible, four-dimensional, non-compact space, but you'll be able to show that its fundamental group at infinity is non-trivial.
Not even exotic R4, just
Exactly. Exactly, looks nothing like R4 at all, exactly. And I think to that point, I think it's an interesting question. I think it's unknown whether there are any exotic R4s that cover a compact four manifold at all. Yeah, that's a good question.
If you point out that possibility to Borel, would he phrase this question differently? I mean, in others. I mean, when you say aspherical manifold, perhaps he was thinking quotient of
Yeah.
quotient of RE.
Yeah, I don't know. I mean, it took basically 30 years from the time Borel was asking this question to the point where Davis even produced the first examples of aspherical spaces manifolds not covered by Rn. So I guess I'd be curious to know sort of what the expectations were about whether they expected there to be something even stronger be true, that perhaps the covers do have to be Rn. I don't know. It's sort of true in some contexts in higher dimensions, at least for the tori and stuff, like you said. But yeah, I don't know. It's a good question. Actually, sorry, maybe one last plug to answer, not to answer that, but to insert. Shmuel Weinberger has a really nice book on it's called Variations on a Theme of Borel, and it explores both sort of like the history and all the sort of different branches of this. So it's a really nice book. Is it a question over there or just a head scratch? Question or no? Okay, cool. Oh. Yeah. Of x and x prime themselves. So I think the best way to think about their fundamental group is to think about like a bit of like a JSJ decomposition of the boundary. So they start with a knot in boundary of the Maser quark. That's some integer homology sphere. It's got some interesting fundamental group though, and you're taking this knot complement in it. And this turns out to be a hyperbolic knot in that. So it's going to be, nothing's going to get too clean or simple with the fundamental group. So you got this piece that looks like a knot complement in a integer homology sphere. So there's some basic constraints on that. And then what does the rest look like? You've sewn in, I mean, this part disappears. And so on the other side of that torus, you now see a S1 from the D2 factor cross punctured surface. So you'll see like a Z2 a Z star Z times Z. No, that's too many. No, I guess that's right. Yeah, something like that. So yeah, you'll sort of have these two different components to it if you look at the JSJ decomposition. I don't know if that addresses that, but it's somewhat gnarly. So not exactly. So this is why it's so counterintuitive. If we look at any preferred tile, maybe at first it seems like it could be part of some tree or something that we're just growing these on like this. But what you'll notice is eventually all of its boundary faces have to be sort of closed up. And not only that, but all of its lower dimensional edges are also now going to be joining into, so it really is going to be completely kind of engulfed, not like in a tree-like way. So what Davis proves is basically this, the aspherical condition, sorry, not the aspherical condition, the flag condition on the triangulation, it just really ensures that when you look at this, I mentioned this word length on the set of tiles, you can decompose your faces of your building block. Sorry, for a given word element in my Coxeter group, I have some tile x. And so for that particular copy of x, some portion of my faces are sort of outward pointing in the sense that their neighbor is longer in the word length. And then some of them are inward facing in the sense that their neighbor is shorter. And so which faces are which are going to vary based on where you are in the Coxeter group. But the point is that the collection of inward ones Davis proofs sort of combinatorially will always be a PL disk. It just sort of, you know, he just sort of, I don't know the best way to put it, but it involves the Coxeter group's you know, structure. When you look at sort of neighbors, they sort of form kind of like a sink in some sense. I don't know if that answers that. Yeah, great question. So it appears totally not specific. In fact, if you want to try to do an infinite version of this, one nice thing you can do is take like Gauss's infinite order quarks, and you can actually reproduce exactly this. You can get a pair. The problem actually comes with the obstruction. So here we were using like a really binary type of obstruction, like can or cannot contain a torus of a certain genus. If you want, for example, this isn't the main question you're asking, but if you wanted to perhaps use a different construction because you wanted infinitely many, the main problem now is like I need some invariant on the covers that can distinguish infinitely many. And so while there's lots of different inputs you can play around with, the hard part is finding an input and an obstruction on the cover. So yeah, you can also, you know, you can choose non-aspherical inputs and you can get some interesting manifolds that way. So there's lots of things in the recipe that still work. It just depends what one's goal is.